Hello, and welcome to Space for Sleep. Nebulae are not decorations placed between the stars. They are the visible breath of the galaxy. A nebula can look soft in a telescope image, a red cloud, a blue veil, a dark horse-shaped silhouette, a glowing ring, a torn shell of light left behind by an exploded star. But the softness is deceptive. These are structures of gas, dust, radiation, gravity, chemistry, shock waves, magnetic fields, and time. Some are cold enough that molecules can survive in their interiors. Some are hot enough that atoms are stripped apart. Some are nurseries where stars are assembling from darkness. Some are the remains of stars that have died and returned their material to space. Some preserve the quiet beginning of a planetary system. Others preserve the violent end of a massive star. A star is born from a cloud. It spends its life changing simple elements into more complex ones. Then, one way or another, it gives material back. A low or intermediate mass star sheds its outer layers and leaves a glowing planetary nebula around a white dwarf. A massive star dies violently, throwing oxygen, silicon, iron, dust, and shock-heated gas back into the interstellar medium. The returned material mixes with older gas, cools, gathers, and eventually becomes part of another molecular cloud. From that cloud, new stars form, and around some of those stars, disks form, and in those disks, planets form. This is not a metaphor. It is the operating cycle of a galaxy. Nebulae are where that cycle becomes visible. They show matter before it becomes a star, while it is becoming a star, after it has been processed by a star, and after it has been scattered by a star's death. They are among the most beautiful objects in astronomy because they are among the most physically rich. Their colors are not random. Their shapes are not accidental. A bright rim tells you where ultraviolet radiation is striking dense gas. A dark lane tells you where dust is blocking starlight. A blue reflection nebula tells you that small grains are scattering shorter wavelengths more efficiently. A red emission nebula tells you that hydrogen is recombining after being ionized by young massive stars. A tangled supernova remnant tells you that a shock wave is still expanding through space centuries or millennia after a star destroyed itself. This is what makes nebulae more interesting than a simple gallery of cosmic clouds. Every type of nebula answers a different question. Where do stars come from? What happens to a cloud when the first massive stars ignite inside it? How does dust hide a future star before it is born? How does a dying star return carbon and nitrogen to space? How does a supernova shock wave keep moving centuries after the explosion? Why do telescope images use colors the human eye would never see? A good nebula story is therefore not only visual. It is a detective story told in light, shadow, chemistry, and motion. The subject is easy to make pretty and very easy to make shallow. But nebulae deserve more than a gallery of beautiful images. They are not just things to look at. They are evidence. They are laboratories. They are records of stellar birth, stellar death, chemical enrichment, planet formation, and galactic evolution. So we will move through them carefully. Molecular clouds, emission nebulae, reflection nebulae, dark nebulae, planetary nebulae, supernova remnants, and the new infrared views that Webb has brought to all of them. The goal is not simply to name famous objects. The goal is to understand what they are showing us. A nebula is where the galaxy turns matter into stars and stars back into matter. The interstellar medium, the material filling the space between stars, is the substrate from which nebulae emerge and into which they eventually dissolve. Understanding nebulae requires first understanding the medium they exist within. The interstellar medium is not empty, though in human terms it is extraordinarily rarefied. In the densest parts of the galaxy's interstellar medium, the molecular clouds, there are perhaps 100,000 to 1,000,000 molecules per cubic centimeter. In the average interstellar medium, The density is closer to 1 atom per cubic centimeter. In the hot, diffuse gas that fills much of the interstellar volume, the density is less than 1 atom per cubic centimeter. The best vacuum achievable in an Earth laboratory is still far denser than this. By the standards of any process observable at human scales, the interstellar medium is essentially nothing. And yet over the enormous volumes of interstellar space, parsecs, tens of parsecs, hundreds of parsecs in extent, even this extraordinarily thin material accumulates into masses equivalent to thousands to millions of times the mass of the Sun. These are the giant molecular clouds, the reservoirs from which stars form, and the cold, dark interiors of the densest of them represent the closest thing the galaxy has to a fertile ground for the emergence of new solar systems. The interstellar medium exists in several distinct phases, as discussed in the Milky Way episode: the cold neutral medium, the warm neutral medium, the warm ionist medium, and the hot ionist medium, each characterized by different temperatures and densities and shaped by different heating and cooling mechanisms. Nebulae visible to telescopes typically represent the densest, most structured regions of this medium. The molecular clouds and their associated features, the regions of ionist gas surrounding newly formed massive stars, the shells and filaments of supernova remnants, and the stellar ejecta of dying stars. Most of the interstellar medium's mass is in hydrogen, either atomic hydrogen, written H1 and pronounced H1, or molecular hydrogen, H2, or ionist hydrogen, H2. The balance between these phases depends on temperature, density, and the intensity of the ultraviolet radiation field from nearby stars. Understanding which phase dominates in which environment is central to understanding where and how stars form, because only in the molecular hydrogen phase, cold, dense, shielded from disruptive ultraviolet radiation, can gravity successfully pull material together faster than thermal pressure can push it apart. Tracing the different phases of the interstellar medium requires different observational techniques. Atomic hydrogen emits a characteristic radio signal at a wavelength of 21 centimeters, produced by the spin-flip transition of the hydrogen atom's electron between two closely spaced energy levels. This emission penetrates even the densest dust clouds without absorption and can be detected throughout the entire galaxy, making 21-centimeter radio observations the primary tool for mapping the large-scale structure of neutral hydrogen in the Milky Way and in other galaxies. Molecular hydrogen, the dominant constituent of molecular clouds, is unfortunately very difficult to observe directly because H2 lacks the asymmetric charge distribution needed for efficient radio emission at typical molecular cloud temperatures. Instead, molecular clouds are traced primarily by carbon monoxide, CO, which is abundant in molecular environments and emits at convenient millimeter wavelengths detectable by radio telescopes. Ionist hydrogen, the H2 regions associated with young, massive star clusters, emits at specific optical wavelengths corresponding to the recombination of free electrons with protons, producing the characteristic red glow of hydrogen alpha emission that makes emission nebulae so visually distinctive in photographs. X-ray emission from the hot, shocked gas of supernova remnants is detectable by space-based X-ray telescopes. Dust, which permeates most dense interstellar environments and is responsible for the dark appearance of dark nebulae and the reddening of stars viewed through molecular clouds, emits thermally in the infrared and can be mapped by infrared space observatories like Spitzer and Herschel and now by the James Webb Space Telescope. Dust is one of the quiet main characters in every nebula. It is easy to imagine interstellar dust as ordinary dust, dirty, gray, lifeless powder. In reality, interstellar dust is a population of tiny solid particles, often smaller than a micrometer, made of silicates, carbon-rich material, metallic grains, and icy mantles in cold environments. These grains are tiny compared with sand, but they dominate the way light moves through dense interstellar regions. They absorb ultraviolet and visible light, scatter blue light, re-radiate absorbed energy in the infrared, provide surfaces for chemical reactions, and help cool gas enough for collapse. Without dust, star formation would be different. Dust shields molecular hydrogen and other molecules from ultraviolet radiation. Dust allows gas to lose heat by emitting infrared radiation. Dust grains provide the surfaces on which molecular hydrogen forms efficiently, and molecular hydrogen is the main constituent of the clouds from which stars form. Dust is therefore not a contaminant in the story of star birth. It is part of the machinery. Dust also explains extinction and reddening. When starlight passes through a dusty cloud, shorter blue wavelengths are scattered and absorbed more strongly than longer red wavelengths. A star behind dust appears dimmer and redder than it really is. This effect once made distance measurements difficult, because an intrinsically bright star behind dust can masquerade as a fainter or cooler star. Modern astronomy turns the problem into a tool. By measuring how much starlight has been reddened, astronomers can estimate how much dust lies along the line of sight and reconstruct the structure of interstellar clouds. In infrared astronomy, the same dust becomes visible. A dark cloud in optical light becomes a glowing structure in far infrared light because the grains, cold though they are, radiate thermal energy. A grain at 20 Kelvin emits mostly in the far infrared and submillimeter. A grain heated near a young massive star emits at shorter infrared wavelengths. Polycyclic aromatic hydrocarbons, large, flat carbon-bearing molecules, often abbreviated PAHs, glow in characteristic mid-infrared bands when struck by ultraviolet photons. These PAH emissions outline the surfaces of molecular clouds where radiation is processing the gas and dust, especially in photodissociation regions. This is why Webb's mid-infrared images of nebulae can look so different from Hubble's optical images. Webb is not simply seeing through dust. It is seeing the dust itself and the molecules mixed with it, glowing in ways that visible light telescopes cannot detect. The result is not just a prettier picture. It is a different physical map of the same region. Dust can also become the beginning of planets. In a protoplanetary disk, microscopic grains collide, stick, settle toward the disk midplane, grow into aggregates, and eventually become the seeds of planetesimals. The grains that begin as interstellar dust are altered, melted, coated with ice, fragmented, and reassembled in the disk, but the continuity is real. A nebula's dust is not separate from the dust that later becomes asteroids, comets, and rocky planets. The next time a nebula appears as a dark lane across a glowing cloud, it is worth remembering that the darkness is not an absence. It may be the densest and most future-rich part of the image. These multiple observational windows onto the interstellar medium and its nebular structures provide complementary views of the same underlying physical environments, each revealing aspects invisible to the others. A molecular cloud that is completely dark at optical wavelengths, opaque to visible light due to dust absorption, may glow brilliantly in radio CO emission, infrared dust emission, and potentially X-ray emission if a massive star within it has begun ionicing its surroundings. The comprehensive picture requires all these wavelengths. There is a special caution needed when talking about nebulae. The images are real, but they are not simple photographs in the ordinary human sense. Many nebula images are made by combining observations taken through different filters. A telescope might observe hydrogen alpha emission, oxygen 3 emission, sulfur 2 emission, infrared dust emission, or X-rays from shock gas. Those data are then mapped into visible colors so that the structures can be seen and compared. Sometimes the color mapping approximates what a human eye might see if it were sensitive enough. Sometimes it is deliberately false color, not because it is fake, but because the wavelengths being shown are invisible to the human eye, or because different emission lines need to be separated visually. The famous Hubble palette, often used for emission nebulae, maps sulfur, hydrogen, and oxygen emission into red, green, and blue channels. This can make hydrogen-rich clouds look green or gold rather than the deep red they would appear in a more natural visible light rendering. Webb images often combine near-infrared or mid-infrared wavelengths, which human eyes cannot see at all, into visible colors chosen to represent differences in temperature, dust, molecular emission, or stellar populations. A blue star in a Webb image may not mean blue visible light. A red filament may not be visibly red. The color is a language, not a lie. This matters for trust. A nebula image is not fantasy art. It is data made visible. The important question is not whether the eye could see exactly those colors, but what physical information the image is encoding. In a good nebula image, every color has a reason. Red may trace warm dust. Green may trace sulfur or molecular hydrogen. Blue may trace hotter stars or shorter infrared wavelengths. Dark regions may not be empty space, but dust so dense that it blocks background light. The beauty of a nebula image is therefore inseparable from the measurement behind it. This is why multi-wavelength astronomy is so powerful. The same object can look completely different in visible light, infrared, radio, ultraviolet, and X-rays. A dark cloud in optical light may glow in millimeter emission from carbon monoxide. A smooth red nebula in hydrogen alpha may reveal embedded protostars in infrared. A supernova remnant that looks like a faint shell in optical light may blaze in X-rays where shocked gas reaches millions of degrees. No single wavelength gives the full truth. A nebula is a layered object, and each type of light opens a different layer. One of the quiet revolutions of modern astronomy is that the public has learned to recognize these multi-wavelength portraits as part of the natural language of science. When we look at a Webb image of a star-forming region, we are not seeing what a spaceship window would show. We are seeing what matter, dust, radiation, and chemistry are doing at wavelengths our eyes never evolved to detect. Giant molecular clouds are the largest discrete structures in the interstellar medium and the principal nurseries of star formation throughout the galaxy. A typical giant molecular cloud has a mass of roughly 10,000 to 10 million times the mass of the Sun, a linear extent of roughly 10 to 100 parsecs, 30 to 300 light-years, and an average density of roughly 100 to 1,000 hydrogen molecules per cubic centimeter. The temperature in the interior of a dense molecular cloud is extraordinarily cold by astrophysical standards, 10 to 30 Kelvin, only 10 to 30 degrees above absolute zero. At these temperatures, the thermal kinetic energy of the gas molecules is very low, and a wide range of chemical reactions that would be far too slow at higher temperatures can proceed efficiently when driven by cosmic rays, surface chemistry on dust grains, or the accumulated time of millions of years of cold cloud evolution. This cold interior environment is chemically remarkable. More than 200 distinct molecules have been detected in interstellar molecular clouds through their radio emission or absorption, ranging from simple diatomic molecules like hydrogen, H2, carbon monoxide, CO, molecular nitrogen, N2, and water, H2O, to complex organic molecules including methanol, formaldehyde, formic acid, acetaldehyde, glycolaldehyde, and even amino acid precursors and other biologically relevant molecules in some cases. The molecular complexity of the interstellar medium, the diversity of chemical species present in cold, dark molecular clouds, is one of the more surprising discoveries of radio astronomy, reflecting the extraordinary efficiency of chemistry on the surfaces of interstellar dust grains at very low temperatures over very long timescales. The chemical complexity of molecular clouds has direct implications for the formation of planets and the preconditions for life. When a molecular cloud core collapses to form a protostellar disk, the rotating disk of gas and dust from which planets eventually assemble, it carries with it part of the molecular inventory of the parent cloud, including water, carbon-bearing molecules, nitrogen-bearing molecules, and chemical precursors relevant to later prebiotic chemistry. The specific chemical environment of the parent molecular cloud, therefore, shapes the initial chemical inventory of the forming planetary system, potentially influencing what materials are available when planets assemble and their surfaces are first being processed. Molecular clouds are not uniform, smooth objects. They are hierarchically structured, organized into filaments, clumps, and cores across a range of scales, with the densest, most compact cores representing the sites where star formation actually initiates. This filamentary structure, now imaged in exquisite detail by the Herschel Space Observatory and by ground-based millimeter and submillimeter telescopes, appears to be a universal feature of molecular clouds across the galaxy, driven by a combination of turbulence, magnetic fields, and gravity. The dense filaments of molecular clouds channel material toward higher density knots, and within the densest of these knots, protostellar cores, gravity eventually wins over thermal pressure and turbulence, and collapse begins. The chemistry inside molecular clouds is one of the reasons nebulae matter far beyond stellar astronomy. At first glance, a molecular cloud seems too cold and too thin to be chemically active. The temperature is often only 10 Kelvin. The density, while high by interstellar standards, is still closer to a vacuum than to any gas we encounter in daily life. But the cloud has time, shielding, dust grains, and cosmic rays. That combination changes everything. Dust grains act like tiny chemical surfaces. Atoms and simple molecules stick to them, migrate across them, meet other atoms and molecules, and react. Hydrogen atoms become molecular hydrogen. Oxygen and hydrogen can become water ice. Carbon monoxide can freeze onto grains and be transformed through successive hydrogen additions into methanol. More complex organic chemistry can build up in icy mantles on the dust grains, especially when ultraviolet photons and cosmic rays process those ices over long periods. Later, when a protostar forms and warms the surrounding material, some of these molecules evaporate back into the gas phase, where radio and infrared telescopes can detect them. This does not mean that molecular clouds are alive or that they contain biology. They do not. But they contain chemistry that is relevant to the material basis of planets. Water, carbon-bearing molecules, nitrogen-bearing molecules, and organic precursors do not first appear on the surface of a young planet. Some of them are already present before the planet exists, inherited from the cold molecular cloud and the protoplanetary disk that forms from it. That inheritance is one of the deep connections between nebulae and life. The chemistry that later becomes part of comets, asteroids, icy moons, planetary atmospheres, and prebiotic environments begins in some form in interstellar clouds. A forming solar system is not chemically blank. It receives a starting inventory. The exact continuity from cloud chemistry to planet chemistry is complex. Some molecules survive collapse and disk formation. Some are destroyed and rebuilt. Some are altered by heat, radiation, shocks, and aqueous chemistry inside asteroids. But the broad picture is clear. Nebulae are not only star nurseries. They are also chemical nurseries. The raw ingredients that eventually become planets are conditioned before the planets form. The process by which a region of a molecular cloud collapses under its own gravity to form a star is called protostellar collapse, and it is governed by a competition between gravity, thermal pressure, turbulence, and the magnetic field that threads through the cloud. For a region of a molecular cloud to collapse under gravity, its self-gravity must be strong enough to overcome the outward thermal pressure pushing the gas apart. The critical mass above which a given region will spontaneously collapse, called the Jeans mass, after the British physicist James Jeans, who calculated it in 1902, depends on the temperature and density of the gas. At the very low temperatures of molecular cloud interiors, the Jeans mass is typically a few solar masses or less, meaning that relatively small, compact regions, molecular cloud cores, are the most prone to gravitational collapse under conditions representative of typical molecular clouds. The collapse of a protostellar core is not instantaneous. It begins slowly, with the outer parts of the core falling inward at subsonic speeds, while the densest central region collapses first and most rapidly. As material falls inward, the growing protostellar object at the center heats up. Gravitational potential energy is converted to thermal energy, and radiation pressure from this heating eventually begins to resist further collapse. The protostellar object's temperature rises. It begins emitting increasingly energetic radiation, and the surrounding infalling envelope of gas and dust gradually becomes optically thick, trapping this radiation and further heating the interior. The earliest stages of protostellar evolution are hidden within the enveloping cloud, invisible at visible wavelengths, but detectable as compact sources of infrared emission from the heated dust surrounding the forming star. A rotating molecular cloud core will conserve angular momentum as it collapses, causing the rotation rate to increase dramatically, the same effect that makes a spinning figure skater accelerate when they draw in their arms. The centrifugal force associated with this rapidly increasing rotation eventually halts collapse in the equatorial plane while allowing collapse to continue along the rotation axis, producing the flattened, rotating protostellar disk, the protoplanetary disk, surrounding the central protostar. This disk is the birthplace of planetary systems, and its formation is an inevitable consequence of the angular momentum already present in the parent cloud core. The radiation from the central protostar, and later from the more energetic central star as nuclear ignition approaches, begins to reverse the infall of the surrounding envelope. Bipolar outflows, jets, and winds launched from the protostellar disk along the rotation axis clear channels through the surrounding infalling material, and eventually the stellar radiation pressure becomes strong enough to halt accretion entirely. The envelope of material surrounding the young stellar object is dispersed, and for the first time the new star becomes visible at optical wavelengths, emerging from the cocoon of the molecular cloud. This emergence can take from a few 100,000 years for the most massive stars, which evolve rapidly and reach the nuclear burning stage while still deeply embedded in their parent clouds, to a few million years for solar mass stars, and tens of millions of years for the least massive stars. The initial mass function, the statistical distribution of masses among newly formed stars, is weighted heavily toward low masses. Most stars that form in molecular clouds are far less massive than the Sun, with masses of a few tenths of a solar mass. Massive stars, 10 times the mass of the Sun or more, are far rarer but disproportionately influential in shaping the environment of the cloud from which they form, as their ultraviolet radiation ionizes and eventually destroys the surrounding molecular material. The earliest stages of star formation are hidden, and that hiddenness is part of the reason nebulae were misunderstood for so long. A protostar is not born as a bright point that immediately shines like an ordinary star. It begins buried. The surrounding envelope of gas and dust absorbs visible light, reprocesses the energy into infrared radiation, and makes the object difficult or impossible to see with optical telescopes. This is why infrared astronomy changed star formation science so profoundly. Infrared light can pass through dust more effectively than visible light, and dust that has been warmed by an embedded protostar glows brightly at infrared wavelengths. A region that looks empty or dark in visible light can become crowded with young stars when seen in infrared. Astronomers classify young stellar objects by how much of their light comes from the central object and how much comes from the envelope and disk around it. In the youngest, most deeply embedded stages, called Class 0 and Class 1, the forming star is still gathering most of its mass. The envelope dominates the emission. The object is surrounded by infalling material, and the disk is still growing. In the later Class 2 stage, the envelope has largely cleared, but a thick protoplanetary disk remains. This is the stage often associated with T-Tauri stars, young, variable, magnetically active stars surrounded by disks where planet formation can begin. In Class 3, the disk has thinned or mostly dispersed, and the young star is approaching ordinary main sequence life. This sequence is not always clean. Real systems are messy. Disks can be viewed edge-on, hiding the star. Envelopes can be asymmetric. Nearby massive stars can strip disk material away. Binary companions can carve gaps or truncate disks. Jets can clear cavities through the envelope and make the system look more evolved in one direction than another. But the broad sequence is real. A star emerges from cloud to envelope to disk to exposed young star. The jets are especially important because they reveal that star formation is not simply collapse inward. As material spirals through a disk toward the protostar, magnetic fields can launch some fraction of that material outward along the rotation axis in narrow, high-speed jets. These jets slam into the surrounding cloud, heating it and creating glowing knots called Herbig-Haro objects. Some Herbig-Haro jets extend for light years, marking the direction of outflow from a protostar that may still be invisible inside its dusty envelope. This is one of the elegant balances in star formation. Material must fall inward to build a star, but angular momentum has to go somewhere. The disk and jets provide a way for the system to shed angular momentum while still allowing mass to accrete onto the central object. Without this regulation, the collapse would not produce a normal star and disk in the way we observe. Planet formation begins before the star is fully settled. Dust grains in the disk collide and stick. Tiny particles become larger aggregates. Larger aggregates become pebbles, planetesimals, and eventually planetary embryos. The disk's temperature gradient determines where volatile materials can freeze. Inside the snow line, rocky material dominates. Beyond it, water ice and other volatiles increase the available solid mass, helping giant planets form. In this sense, the story of a nebula does not end when a star ignites. The same collapsing cloud also creates the architecture from which planets may emerge. When Webb looks into a dusty star-forming region and reveals embedded young stars, it is therefore seeing more than stellar birth. It is looking at the opening stages of planetary system formation. Some of the points inside those clouds may have disks that will make planets. Some will lose their disks too quickly. Some will form brown dwarfs instead of stars. Some will be disrupted by nearby massive stars. The nebula is not producing one outcome. It is producing a population, and every member of that population carries a different future. The most visually spectacular nebulae, the ones that fill astronomical image galleries and dominate public perceptions of what the galaxy looks like, are the emission nebulae, regions of ionized gas surrounding or near newly formed massive stars, glowing in characteristic colors produced by the recombination of ions and electrons after ionization. The physics of an emission nebula is relatively straightforward in its basic outline. a newly formed massive star, an O-type or B-type star, with surface temperature of 20,000 to 50,000 Kelvin or more, emits copious ultraviolet radiation in the far UV range, where photon energies exceed the ionization threshold for hydrogen. These photons ionize the surrounding hydrogen gas, stripping electrons from protons and creating a plasma of protons and electrons. When an electron recombines with a proton, it typically cascades down through a series of energy levels before reaching the ground state, emitting photons at specific wavelengths corresponding to the energy differences between the levels. The most prominent of these, the hydrogen alpha line at a wavelength of 656 nanometers in the red part of the visible spectrum, is what gives emission nebulae their characteristic pink-red color in photographs. The region of ionized hydrogen around a hot star, called an H2 region, pronounced H2 region, expands into the surrounding neutral gas as the star continues to ionize its surroundings. The boundary between the ionized and neutral gas, the ionization front, advances outward until the rate at which the star is producing ionizing photons is balanced by the rate at which protons and electrons are recombining within the ionized volume. The resulting equilibrium structure, called a Strömgren sphere after the Danish-American astrophysicist Bengt Strömgren, who first calculated it in 1939, has a radius that depends on the luminosity of the ionizing star and the density of the surrounding neutral gas. Real emission nebulae are far more complex than the idealized Strömgren sphere of the textbook calculation. They are bounded not by a smooth sphere but by the irregular, clumpy structure of the surrounding molecular cloud, with fingers and columns of denser gas, resisting ionization longer than the surrounding lower-density material. Radiation pressure from the ionizing star and the thermal pressure of the hot, ionized gas drive shocks into the surrounding molecular material, compressing it and potentially triggering new star formation in the compressed zone, a process called radiation-driven star formation or triggered star formation. The morphology of emission nebulae, their pillars, their bright rims, their elephant trunk structures, is largely determined by this interaction between ionizing radiation and structured molecular cloud material. Feedback is one of the key ideas that turns nebulae from static clouds into dynamic systems. In astronomy, feedback means that stars change the environment from which they formed. Low-mass stars do this gently, through jets, winds, and radiation. Massive stars do it violently. An O-type star can emit more ultraviolet radiation than thousands of sun-like stars combined. A cluster of massive stars can carve a cavity into a molecular cloud, drive expanding bubbles of hot gas, compress surrounding material into new filaments, and finally explode as supernovae, adding shock waves to the process. Feedback can be negative or positive, depending on location and timing. It is negative when radiation and winds disperse gas that would otherwise form more stars. It is positive when compression from an expanding shell pushes a region over the threshold for gravitational collapse. Both can happen in the same nebula. A pillar may be eroded on the outside while a dense core inside it collapses. A shell may sweep up gas and trigger stars along its rim, while also clearing the central cavity of material. This dual role explains why star-forming regions can look contradictory. The same massive stars that make a nebula glow are also destroying it. The same shock that disrupts one cloud may compress another. The same radiation that ends star formation in one pocket may begin it in another. Star formation is not a simple on-off process. It is a feedback-regulated cycle in which gravity and energy continually reshape one another. On galactic scales, feedback helps regulate how fast galaxies turn gas into stars. Without feedback, molecular gas might collapse too efficiently, producing stars faster than observed. With too much feedback, star formation would be suppressed too strongly. Real galaxies appear to operate in a balance. Gas cools and collapses, stars form. The most massive stars inject energy and momentum, clouds are disrupted, gas is stirred, and later it can cool again. Nebulae are the local, visible pieces of that galactic regulation system. This is why a single emission nebula can be important beyond its own beauty. It is a nearby example of the process that controls star formation in galaxies across cosmic time. There is another part of nebula science that is easy to miss in public images: the measurements behind the images. A nebula photograph can show shape, but shape alone is not enough. Astronomers want to know distance, mass, temperature, density, velocity, chemical composition, magnetic field structure, radiation environment, and age. None of these properties is written on the image. They have to be inferred. Distance is often the first problem. For nearby star-forming regions like Orion or Taurus, the Gaia spacecraft has transformed the field by measuring precise parallaxes for young stars associated with the clouds. If the stars embedded in or near a nebula are at a known distance, the nebula can be placed at roughly the same distance. For more distant nebulae, astronomers use stellar associations, radial velocities, extinction, masers, and the structure of the Milky Way to estimate where the cloud lies. Distance matters because it turns apparent size into real size and apparent brightness into real luminosity. A nebula cannot be understood physically until its distance is known. Mass is inferred from gas and dust tracers. Molecular clouds are often weighed through carbon monoxide emission, using a conversion factor that relates CO brightness to molecular hydrogen mass. This conversion is powerful but imperfect because CO abundance and excitation vary with environment. Dust emission provides an independent estimate. If the dust temperature and opacity are known, infrared brightness can be converted into dust mass and then into gas mass using an assumed gas-to-dust ratio. In dense cores, still other tracers are needed because CO can freeze onto dust grains and become less reliable. Every mass estimate carries assumptions, and part of nebula science is understanding those assumptions well enough to compare regions honestly. Temperature can mean different things. Gas temperature, dust temperature, electron temperature in an H2 region, shock temperature in a supernova remnant. Each is measured differently. Molecular line ratios reveal gas conditions in cold clouds. Infrared colors reveal dust temperature. Optical emission line ratios in ionized nebulae reveal electron temperature and density. X-ray spectra reveal the temperature of million-degree shocked gas. A single nebula may contain 10 Kelvin molecular gas, 100 Kelvin photodissociation regions, 10,000 Kelvin ionized gas, and million-degree X-ray plasma, all in one physical system. Velocity is measured through Doppler shifts. A spectral line shifted slightly toward shorter wavelengths indicates gas moving toward us, shifted toward longer wavelengths, gas moving away. By mapping these shifts across a nebula, astronomers can reconstruct expansion, rotation, outflows, turbulence, and shock motion. In planetary nebulae, velocity maps show shells expanding from dying stars. In molecular clouds, they reveal filaments feeding dense cores. In supernova remnants, they show ejecta moving at thousands of kilometers per second and shocks slowing as they sweep up surrounding material. Chemical composition is read from spectral fingerprints. Hydrogen, oxygen, nitrogen, sulfur, carbon monoxide, molecular hydrogen, PAHs, silicates, water ice, and dozens of other species leave features at specific wavelengths. This is one of the reasons nebulae are so scientifically generous. They do not merely glow, they announce the atoms and molecules doing the glowing. A spectrum turns a beautiful cloud into a chemical inventory. Magnetic fields are harder to measure but deeply important. Molecular clouds are threaded by magnetic fields that can resist collapse, guide flows, align dust grains, and influence filament formation. Polarization measurements reveal these fields indirectly. Dust grains tend to align with magnetic fields, and the light emitted or absorbed by those grains becomes polarized. By mapping polarization, astronomers can infer the orientation of the magnetic field across a cloud. The result is often striking. Filaments, cores, and magnetic fields are not randomly arranged. Gravity, turbulence, and magnetism are all involved in shaping the cloud. This is where the quiet image becomes a physical system. A nebula is not only red or blue or dark. It has a three-dimensional structure, a velocity field, a chemistry, a temperature map, a density distribution, and an evolutionary history. The image is the doorway. The measurements are the room behind it. The Orion Nebula, M42, is the nearest large emission nebula to Earth and the most extensively studied star-forming region in the sky. Located roughly 1,300 light-years away and visible to the naked eye as the fuzzy middle star of Orion's sword. The Orion Nebula is the visible face of a much larger, denser molecular cloud, the Orion Molecular Cloud, extending behind it. The visible nebula is ionized by a cluster of young, massive stars called the trapezium, for brilliant O-type and B-type stars packed into a region less than 1.5 light-years across, whose combined ultraviolet luminosity ionizes an enormous volume of the surrounding gas. Hubble observations of the Orion Nebula in the 1990s revealed an extraordinary detail. The nebula is filled with proplyds, a term derived from protoplanetary disk, compact, teardrop-shaped structures in which newly forming protoplanetary disks are being photoevaporated and ionized by the intense ultraviolet radiation from the nearby trapezium stars. These proplyds represent planetary systems in the process of being destroyed by their environment. The intense radiation from the nearby massive stars is ablating material from the outer portions of the disks at rates that, in the most severely irradiated cases, could remove the disk's entire mass within a few million years, potentially preventing any planetary system from forming. The Orion Nebula thus shows both star formation at work. Numerous young stellar objects and protostars are visible throughout the cloud, and the environmental destruction of potential planetary systems by the harsh radiation field of nearby massive stars. The Hubble Orion observations also produced one of the most statistically important results in early exoplanet science. A census of the fraction of young stars with protoplanetary disks, which established that a large majority of young stars in star-forming regions possess disks in their first few million years, providing direct evidence that the potential for planetary system formation is common. The Orion region is especially important because it contains multiple stages of star formation in one nearby complex. The bright Orion Nebula is only the illuminated surface. Behind it and around it lies the much larger Orion Molecular Cloud Complex, including Orion A and Orion B, dark clouds, reflection nebulae, embedded clusters, protostars, filaments, and young stars at many evolutionary stages. This makes Orion one of the most valuable natural laboratories in the sky. It is close enough for individual young stars and disks to be resolved, rich enough to contain massive star feedback, and complex enough to show how one cloud can produce multiple generations of stars. The Orion Bar, a bright ridge near the edge of the Orion Nebula, is a textbook photodissociation region. It marks the transition from ionized gas exposed to ultraviolet radiation through atomic gas into molecular gas protected deeper in the cloud. Before Webb, many of these layers were inferred but not cleanly resolved at small scales. Webb's infrared observations have shown the interface to be much more structured than a smooth, two-dimensional wall. Folded surfaces, ridges, globules, and sharp transitions between ionized, atomic, and molecular material. This matters because photodissociation regions are everywhere in star-forming galaxies. Orion lets astronomers study one of them close enough to understand the physics in detail. The proplyds of Orion are equally important. Each one is a young planetary system exposed to an intense environment. A protoplanetary disk around a young star would, in isolation, evolve quietly over a few million years, allowing dust and gas to assemble into planets. But in Orion, many disks sit near massive O-type stars whose ultraviolet radiation heats and strips away gas from the disk surface. The result is a glowing teardrop shape, the disk and young star at the head, ionized material streaming away in a tail. This is not only beautiful, it changes planet formation. A disk losing gas quickly may still form rocky planets, but giant planet formation may become harder because giant planets require gas envelopes before the disk disperses. The environment of a star's birth can therefore influence the architecture of the planetary system that forms around it. Stars are not born in isolation. The neighbors matter. This makes Orion a humbling place to study. We often imagine a solar system as something private. One star, one disk, planets forming quietly. Orion reminds us that many stars are born in crowded, irradiated nurseries where nearby massive stars can shape, erode, and sometimes prematurely in the planet-forming material around smaller stars. Our own sun may also have formed in a cluster, perhaps near massive stars whose supernovae contributed short-lived radioactive isotopes to the early solar system. In that sense, studying Orion is also studying a possible environment of our own origins. James Webb Space Telescope observations of the Orion Nebula released in 2022 pushed the view of this region to entirely new depths of detail. Webb's infrared cameras revealed structures within the nebula invisible at the optical wavelengths where Hubble operates, including the internal structure of the proplyds and infrared light that penetrates the dust, new categories of compact emission sources that may represent very young brown dwarf companions, and detailed morphology of the interface between the ionized nebula and the neutral molecular material behind it that revealed complex physical processes at the ionization front operating, at scales previously inaccessible to observation. The pillars of creation in the Eagle Nebula, M16, are perhaps the most iconic nebular structures ever photographed, and their story illustrates both the beauty and the violence of star-forming regions. The Eagle Nebula is a star-forming complex located roughly 7,000 light-years from Earth in the constellation Serpens. The central star cluster, NGC 6611, contains numerous young, massive stars whose ultraviolet radiation illuminates and is sculpting the surrounding molecular cloud. The pillars of creation are three tall columns of dense molecular material, the tallest about 4 to 5 light-years from base to tip, that protrude from the molecular cloud into the ionized H2 region surrounding the central cluster. The pillar's distinctive form reflects the same physics operating throughout emission nebulae. Dense molecular material resists photoionization longer than its lower density surroundings, creating elongated shadows behind dense clumps and columns that are preferentially eroded on their facing surfaces while their interiors are shielded. The tips of the pillars are bright with emission from the outer ionized layer, while the dark interior, the shadowed molecular column, remains cold, dense, and opaque to visible light. Within these dark interiors, stellar formation may be occurring, or may have recently been interrupted, as the advancing ionization front has compressed the molecular material and potentially triggered the collapse of pre-existing density enhancements. The original Hubble image of the pillars, released in 1995, was taken with the then newly installed Wide Field and Planetary Camera 2, and became one of the most widely distributed scientific images in history, appearing on posters, textbooks, magazine covers, and cultural products ranging from tattoos to coffee mugs. The image combined observations in 3 different emission lines, sulfur-2, hydrogen-alpha, and oxygen-3, mapped to red, green, and blue color channels respectively, creating the greenish-blue color of the pillars and the reddish-orange of the broader nebula. These colors do not represent the actual visible light appearance of the nebula, which would be dominated by the deep red of hydrogen-alpha emission. They are a scientifically informative color mapping that reveals the distribution of different chemical species across the structure. A revised Hubble image of the pillars was released in 2015, made with an upgraded camera providing higher resolution and wider field of view. And then the James Webb Space Telescope produced its own versions of the pillars in 2022, first in near-infrared and then in mid-infrared. The Webb near-infrared image penetrated the dust of the pillars to reveal stars forming within them, including numerous young stellar objects visible as compact red sources embedded within the cloud material. The mid-infrared image revealed the broader emission nebula environment in new detail, showing the distribution of polycyclic aromatic hydrocarbons, large organic molecules that emit characteristically in the mid-infrared, outlining the surfaces of the pillars where photodissociation processes are active. Chandra X-ray Observatory observations of the Eagle Nebula added another dimension. X-ray emission from the young stellar population of NGC 6611, revealing hundreds of young stars in the cluster and documenting the X-ray luminosity of these recently formed objects, which are typically far more X-ray active than older, more settled stars like the Sun. The comprehensive multi-wavelength picture of the Eagle Nebula, radio, infrared, optical, ultraviolet, X-ray, is a demonstration of how much information about a star-forming region can be extracted by combining observations across the electromagnetic spectrum. It is sometimes said that the pillars of creation may already have been destroyed by nearby massive star feedback or a past supernova, and that we are only seeing them because their light left the Eagle Nebula thousands of years ago. The light travel time part is certainly true. We see the pillars as they were when the light began its journey. But the destruction claim is much less certain. Massive stars are eroding the pillars, and they will not survive indefinitely, but the exact timing and mechanism of their future dispersal remain matters of modeling rather than an observed fact. The scientifically safer statement is also the more interesting one. We are watching a temporary structure, sculpted by radiation and winds, being slowly photoevaporated while stars form inside it. Reflection nebulae are clouds of interstellar dust illuminated not by hot, ionising stars, but by nearby, cooler stars whose light they scatter. Unlike emission nebulae, which glow with their own radiation from ionized gas, reflection nebulae simply scatter the light of a nearby star in the same way that Earth's atmosphere scatters sunlight to produce blue sky, by Rayleigh and Mie scattering off dust particles, preferentially in blue wavelengths. The characteristic blue color of most reflection nebulae is a direct consequence of this scattering process. Dust particles in interstellar space preferentially scatter shorter wavelength blue light more efficiently than longer wavelength red light, the same reason Earth's sky is blue. When starlight illuminates a dust cloud, the reflected light that reaches us is enriched in blue relative to the original starlight. The cloud looks blue even if the illuminating star appears white or yellow. Several other famous nebulae help complete the picture because each emphasizes a different physical process. The Rosette Nebula is a large circular emission nebula surrounding a central cluster of young stars. The cluster has blown a cavity in the surrounding gas, producing a flower-like appearance in wide-field images. The rosette is a clear demonstration of how a stellar cluster can hollow out the cloud that gave birth to it. The stars in the center are young, but already their radiation and winds are pushing the remaining gas outward, limiting how much longer the region can continue forming stars. The Lagoon Nebula, M8, is another active star-forming region, visible in the constellation Sagittarius. It contains emission gas, dark lanes, embedded young stars, and compact regions of intense activity. Inside it lies the Hourglass region, a bright knot of ionized gas shaped by massive young stars. The lagoon is valuable because it shows star formation not as one neat object, but as a complex environment of clusters, dust lanes, hot stars, and molecular material overlapping. The Trifid Nebula, M20, is famous because it combines three types of nebula in one object: red emission gas, blue reflection nebulosity, and dark dust lanes that divide the bright region into lobes. Its appearance is therefore a compact visual lesson in nebular physics. Ionized hydrogen glows red. Dust reflecting starlight appears blue. Dense dust blocks light and makes dark lanes. The same object can display different modes of interaction between light and matter. The Veil Nebula, unlike these star-forming regions, is a supernova remnant. Its long, delicate filaments show shock-heated gas from an explosion thousands of years old. The contrast between the lagoon or rosette and the veil is striking. One is the environment of stellar birth, the other the aftermath of stellar death. Both are nebulae. Both glow because energy is moving through gas. But the source of that energy is completely different. This variety is what makes the subject work for a long-form episode. Nebulae are not one thing. The word nebula is a historical umbrella placed over many physically different objects that appeared cloudy or misty to early telescopes. Modern astrophysics separates them by mechanism: cold molecular material, ionized gas, reflected starlight, dust absorption, ejected stellar envelopes, and shocked supernova debris. The old word remains, but the science underneath it has become far richer. The Pleiades star cluster, visible as a tight group of bright stars to the naked eye in the constellation Taurus, provides one of the most famous examples of a reflection nebula. Long-exposure photographs of the Pleiades reveal the cluster to be surrounded and laced through with faint, blue, wispy nebulosity, dust clouds that the cluster happens to be passing through, illuminated by the bright young stars of the cluster. This dust is not physically associated with the Pleiades. It is interstellar material that the cluster is moving through at the current epoch, illuminated only temporarily as the cluster passes. Another famous reflection nebula is the Witch-Head Nebula in the constellation Eridanus, a faint, irregular cloud illuminated by the brilliant blue star Rigel. In long-exposure photographs, the Witch-Head shows a vaguely face-like silhouette that gives it its name, a coincidence of geometry in the dust distribution rather than any intrinsic shape. The M78 complex in Orion is one of the brightest reflection nebulae in the sky, a cluster of dense, blue reflecting dust clouds associated with the broader Orion molecular cloud complex, illuminated by young OB stars embedded within them. M78 also contains numerous young stellar objects at earlier stages of formation than those visible in the Orion Nebula, providing a complementary view of star formation at an earlier epoch. Dark nebulae are molecular cloud structures visible not because they glow but because they silhouette against brighter backgrounds, emission nebulae behind them, or the general stellar background of the galaxy. They are dense enough to absorb essentially all the visible light from background sources, appearing as dark patches or lanes against the luminous regions around them. The Horsehead Nebula, B33 in the Barnard catalog of dark nebulae, is among the most recognizable objects in the sky, a dark protrusion of dense molecular material extending into the bright emission nebula, IC434 behind it, whose shape and silhouette bears a striking resemblance to the head and neck of a chess knight or a horse looking to one side. The Horsehead is part of the broader Orion molecular cloud complex and lies about 1,300 light-years away. It is a region of active star formation. Within the dark molecular material of the Horsehead, several protostars have been identified, though the entire structure will eventually be eroded by the same ultraviolet radiation from the nearby massive star Sigma Orionis that illuminates the Emission Nebula behind it. Hubble and Webb images of the Horsehead Nebula in near-infrared wavelengths that partially penetrate the dust have revealed the internal structure of the dense molecular column, including young stellar objects embedded within it and the complex texture of the cloud's surface where it is being photoeroded. The Webb near-infrared image of the Horsehead released in 2024 showed the top surface of the nebula, the region where the cloud's dense molecular material meets the ionist environment of the surrounding H2 region, in spectacular detail, revealing a landscape of dense gas filaments, molecular hydrogen emission from the photodissociation region at the cloud surface, and the first hints of the complex internal structure of the cloud that radio observations have mapped at longer wavelengths. The Carina Nebula shows the same processes on an even more dramatic scale. Carina is a vast star-forming complex in the southern sky, containing some of the most massive and luminous stars in the Milky Way. Webb's early image of the region, known as the Cosmic Cliffs, became one of the defining first portraits of the telescope, a bright, scalloped wall of gas and dust shaped by young stars above it, with embedded star formation still proceeding inside the darker material. The image looks like a landscape, but the apparent cliff is the edge of a cavity carved into a molecular cloud by ultraviolet radiation and stellar winds. The mist rising from the edge is not mist, but hot ionist gas and dust being photoevaporated from the cloud surface. In Webb's infrared view, dozens of previously obscured young stars appear, jets from protostars cut through the cloud as red streaks. Small features that would be invisible in optical light become signposts of active star birth. The image is beautiful, but scientifically the important point is environmental feedback. Massive stars are both creators and destroyers. Their radiation compresses some gas, possibly triggering collapse in places that were already near instability. The same radiation also erodes the cloud, dispersing the raw material needed for future star formation. A massive star-forming region is therefore a race. Gravity tries to turn cloud into stars, while the first massive stars try to tear the cloud apart. The Tarantula Nebula, also called 30 Doradus, shows what happens when that process is scaled up beyond anything nearby in the Milky Way. Located in the Large Magellanic Cloud, the Tarantula is the most active star-forming region in the local group. If it were as close as the Orion Nebula, it would dominate the night sky. At its center lies the massive star cluster R136, containing some of the most massive stars known. These stars pour out radiation and winds so intense that they carve cavities, compress filaments, and shape the surrounding gas across hundreds of light years. Webb's views of the Tarantula revealed tens of thousands of young stars previously hidden by dust and showed the nebula's cavities and filaments in extraordinary infrared detail. The Tarantula is especially important because its chemical composition is lower in heavy elements than the Milky Way's local star-forming regions. That makes it a useful nearby analog for star formation in the earlier universe, when galaxies were less chemically enriched. By studying the Tarantula, astronomers can learn how massive stars and clusters formed in environments more similar to those of cosmic noon and the young universe. The Lagoon Nebula, the Trifid Nebula, the Rosette Nebula, and the North America Nebula are other nearby examples of the same basic theme: young massive stars illuminating, eroding, and reshaping their natal molecular clouds. Each has its own geometry. The lagoon contains bright emission gas, dark lanes, and active star formation. The trifid combines emission, reflection, and dark nebulosity in a single object, making it a striking demonstration of different nebular processes overlapping in one region. The rosette is a roughly circular cavity around a young cluster, a bubble blown into surrounding gas. The North American Nebula is shaped not because the gas knows anything about continents, but because foreground dust blocks light in a pattern our brains recognize. This is a useful reminder. Names are human. Physics is not. The Horsehead does not know it resembles a horse. The North American Nebula is not shaped by geography. The pillars of creation are not pillars in any architectural sense. These names help us remember, but the structures are made by radiation, density, dust, gravity, and time. The Barnard Catalog, compiled by the American astrophotographer Edward Emerson Barnard in the early 20th century from his pioneering wide-field photographs of the Milky Way, lists numerous dark nebulae as opaque patches against the stellar background. Barnard was one of the first astronomers to systematically document these dark regions as physical objects, regions of genuine opacity, rather than as gaps in the stellar distribution, a conceptual shift that required recognizing that opaque interstellar material could block background starlight. The dark lanes visible along the plane of the Milky Way in wide-angle photographs of the galaxy, the irregular dark patches that interrupt the luminous background of billions of stars, are primarily molecular cloud complexes seen in silhouette, the near-side molecular material of the galaxy absorbing the light of the more distant stellar population. These dark lanes are most prominent along the galactic plane, where molecular cloud complexes are densest, and their irregular, branching structure reflects the filamentary morphology of the molecular cloud network discussed earlier. Some of the most important dark nebulae are not famous for shapes at all. Barnard 68, for example, is a small, dense dark cloud known as a Bok globule. In optical images, it appears almost like a hole punched in the star field, a round patch of darkness with sharp edges, silhouetted against the dense background stars of the Milky Way. It is not empty. It is so dense with dust and cold gas that it blocks the visible light from stars behind it. Infrared observations, however, reveal background stars through the cloud, allowing astronomers to map the dust density inside. Barnard 68 has been studied as a nearly ideal example of a cold, self-gravitating cloud core near the threshold of collapse. Bok globules are important because they represent small-scale star-forming environments. Unlike giant molecular clouds, which can form clusters of many stars, a Bok globule may form one star, a small multiple system, or none at all. Some are stable for long periods. Some are slowly collapsing. Some may have been compressed by external radiation or shocks. Their apparent simplicity makes them useful laboratories for understanding the earliest stages of isolated star formation. Infrared dark clouds are larger and more massive. They appear as dark absorption features against the bright infrared background of the Milky Way, especially in the inner galaxy. These clouds are cold, dense, and massive enough to form clusters and high-mass stars. But many are at stages before those stars have fully ignited and ioniced their surroundings. In other words, they are massive star-forming regions caught before they become bright emission nebulae. They are the quiet before the ultraviolet storm. Dark nebulae also explain why the Milky Way appears split by dark rifts when seen from a truly dark sky. Those rifts are not gaps between stars. They are foreground molecular clouds and dust lanes blocking the star-rich background of the galactic disk. For most of human history, these dark patches were simply part of the visual texture of the sky. Modern astronomy revealed that they are physical structures, nearer than many of the stars they obscure, and often connected to the birth of future stars. There is a lesson in that. Darkness in astronomy is often information. A dark cloud may be dense. A dark lane may mark dust. A missing background may reveal a foreground structure. Not glowing does not mean not important. Planetary nebulae are among the most visually striking objects in the galaxy, and their name, one of astronomy's more enduring misnomers, reflects their appearance through small telescopes rather than their physical nature. When William Herschel and others began cataloging the sky with telescopes in the 18th century, they noticed small, circular, greenish-blue objects that resembled the disk of a planet like Uranus. These objects had no resemblance to any other category of celestial object known at the time, and the term planetary nebula stuck even after it became clear they had nothing to do with planets. A planetary nebula is the ejected outer envelope of a dying intermediate mass star, a star with initial mass between roughly 1 and 8 times the Sun's mass, dispersed into the surrounding interstellar medium during the star's late evolutionary stages. As a star of this mass exhausts its hydrogen fuel and ascends the red giant branch, expanding enormously and cooling, it eventually enters the asymptotic giant branch phase, where thermal pulses drive increasingly strong stellar winds. These winds, over a period of roughly 100,000 to 1,000,000 years, shed a large fraction of the star's outer hydrogen envelope, sometimes reaching mass loss rates around 10,000th to 100,000th of a solar mass per year during the strongest superwind phases. The shed material forms an expanding shell, eventually visible as the nebula, while the exposed stellar core, now denuded of its hydrogen envelope, heats rapidly and begins ionicing the surrounding shell with its intense ultraviolet emission. The illuminated shell of ejected material is the planetary nebula, and the exposed core is the white dwarf at its center. The morphologies of planetary nebulae are extraordinarily diverse: round, elliptical, bipolar, multi-lobed, with jets, with rings, with nested shells, with fine filamentary structure, and the origin of this diversity is an active area of research. The simplest models predict spherical or mildly ellipsoidal shells from a spherically symmetric stellar wind, but the actual observed distribution of shapes is far more complex. The leading explanations for the non-spherical morphologies involve binary stellar evolution, the interaction between the dying star and a close companion, which can focus the mass ejection into equatorial disks and bipolar outflows, and magnetic fields in the stellar wind, which can organize the ejected material along field lines. The frequency of close binary stars among planetary nebula central objects is substantially higher than among ordinary stars, supporting the binary interaction hypothesis. The Ring Nebula, M57, in the constellation Lyra, is one of the most studied and most photographed planetary nebulae. Visible as a tiny, elliptical glowing ring through modest telescopes, it appears as a roughly circular shell of ionized gas about a light-year in diameter at a distance of roughly 2,300 light-years. At its center, the central white dwarf, at roughly 120,000 Kelvin, one of the hottest known stellar objects, is barely visible in deep images. The ring's appearance as a shell rather than a filled sphere is largely a projection effect. We are looking at a roughly spherical or slightly ellipsoidal shell from the outside, and the gas along the line of sight through the center is less compressed than the gas along the shell's edge, making the shell appear brighter at the rim and fainter in the center. The Helix Nebula, NGC 7293, is one of the largest and nearest planetary nebulae, located about 650 light-years away and spanning about 3 light-years in true diameter. It is the largest planetary nebula on the sky, subtending about half a degree, roughly the same apparent angular size as the full moon. Detailed Hubble and Spitzer observations of the helix revealed a complex nested structure of multiple shells and a remarkable population of knots, thousands of compact, comet-shaped dense globules embedded within the Ionis shell. These knots, each roughly as large as the solar system, have bright ionist heads pointing toward the central star and dusty tails shielding behind them, produced by the interaction of the central star's radiation and stellar wind with denser clumps in the ejected material. Their existence reveals that the stellar wind ejection process produces structured, inhomogeneous material rather than a smoothly distributed shell. The Cat's Eye Nebula, NGC 6543, is one of the most morphologically complex planetary nebulae known. Hubble images reveal a nested series of shells, jets, arcs, and knots at different scales, suggesting a long and complicated history of episodic ejection and wind interaction. The bright central region is surrounded by much fainter but extensive outer shells extending many arc minutes across, corresponding to earlier, slower phases of mass loss that predate the formation of the brighter inner nebula. The overall complexity of the Cat's Eye structure has been difficult to explain with any simple model and has been invoked as evidence for the importance of binary interactions in shaping planetary nebula morphology. The Butterfly Nebula, NGC 6302, is one of the most visually dramatic planetary nebulae, with two symmetric lobes of hot gas extending opposite each other from the central star region, the entire structure spanning about 3 light-years. The bipolar morphology, resembling a butterfly or bow tie, results from the ejected material expanding most freely along the polar directions, while an equatorial disk of denser material, formed from an earlier phase of mass loss, constrains the expansion in the equatorial plane. The hot gas within the lobes is being driven by a stellar wind from the extremely hot central star, among the hottest known, at a surface temperature of roughly 250,000 Kelvin, and produces X-ray emission detectable by X-ray telescopes. Planetary nebulae are brief by astronomical standards. The Ionis shell expands and disperses into the surrounding interstellar medium within roughly 20,000 to 100,000 years, a cosmically short interval. After that, the surviving white dwarf, the compact stellar remnant, continues to cool for billions of years, no longer producing sufficient ultraviolet radiation to ionize any detectable surrounding material. The material ejected as the planetary nebula is incorporated into the interstellar medium, enriched with the carbon, nitrogen, and other elements synthesized during the star's lifetime and dredged up to the surface during the asymptotic giant branch phase. These ejected elements are not wasted. They are the contributions of each dying intermediate mass star to the chemical enrichment of the galaxy. Carbon and nitrogen in particular are strongly enriched by stars that pass through giant phases and return material through winds and planetary nebulae. Oxygen is produced mainly in massive stars and spread largely by supernovae, while the broader complexity of organic chemistry depends on many generations of stellar processing and interstellar chemistry. The planetary nebula is the mechanism by which one generation of stars returns its nuclear processing products to the raw material of the next. The future of the Sun belongs to this category, though not in a simple one-to-one way. The Sun is not massive enough to explode as a supernova. It will spend billions more years on the main sequence, slowly increasing in luminosity as hydrogen fusion changes the structure of its core. Eventually, it will leave the main sequence, expand into a red giant, shed mass through stellar winds, and expose its hot core as a white dwarf. Whether the Sun will produce a bright, easily visible planetary nebula has been debated, because planetary nebula visibility depends not only on mass loss, but on how quickly the core heats up before the ejected envelope disperses. Current models generally suggest that the Sun is near the lower mass limit for making a visible planetary nebula, but it may still produce one. though probably a relatively faint and short-lived example compared with the most spectacular nebulae we photograph. The life of the Sun gives a useful scale for understanding planetary nebulae. For now, the Sun is stable because hydrogen fusion in its core supplies outward pressure against gravity. But the hydrogen in the core is finite. Over billions of years, helium accumulates in the core contracts and heats, and the Sun's outer layers slowly respond. Long before the final red giant stages, the Sun's increasing luminosity will alter Earth's climate beyond recognition. By the time the Sun becomes a red giant, Earth will no longer be habitable, regardless of the exact details of the planet's survival. In the red giant and asymptotic giant branch phases, the Sun will lose mass through a dense stellar wind. The outer layers will drift outward. The exposed core will become a white dwarf, extremely hot at first, and its ultraviolet radiation may ionize the surrounding ejected gas. If the timing is right, if the core heats quickly enough before the envelope disperses too far, the result will be a planetary nebula. It may not be as spectacular as the Ring Nebula or the Cat's Eye, but the process will be the same category of event, a Sun-like star returning part of itself to space. This helps remove a common misunderstanding. A planetary nebula is not a planet-forming nebula. It is not a protoplanetary disk. It is not the kind of cloud from which planets are born. It is an old name for the glowing envelope of a dying star. The confusion is unfortunate but historically understandable. Through small telescopes, these objects looked like soft planetary disks, and the name remained. The material returned by stars like the Sun is especially important for carbon and nitrogen enrichment. Massive stars dominate oxygen production and many heavy elements, but intermediate mass stars contribute strongly to the carbon and nitrogen budget of galaxies. Their winds carry products of internal nuclear processing outward. Their planetary nebulae are brief, but their chemical contribution persists. A planetary nebula, therefore, has two meanings at once. It is an ending for one star system and a contribution to many future systems. This future gives planetary nebulae a special emotional weight. They are not only exotic objects around other stars. They are examples of the kind of late stellar transformation our own system will eventually undergo. The Sun will not always be a stable yellow-white main sequence star. The inner solar system will be radically changed. Earth, if it still exists as a physical planet, will be uninhabitable long before the final stages. The outer layers of the Sun will be returned to space, and the remaining white dwarf will cool slowly for billions of years. Webb's image of the Southern Ring Nebula, one of its first public science images, revealed how complicated such a death can be. What looked like a simple glowing shell turned out to contain evidence for a system shaped by companions, dust, and multiple phases of ejection. The central region was not merely a single dying star in isolation. It was a dynamical environment in which stellar companions likely influenced the geometry of the ejected gas. This is increasingly the lesson of planetary nebulae. Many of their most beautiful shapes may be the fossil imprint of binary or multiple star interactions. The Ring Nebula has shown the same complexity under Webb's infrared view. Its main ring is fragmented into dense globules. Its halo contains faint arcs and structures that suggest mass loss was modulated over time, perhaps by companions. A planetary nebula is therefore not only the last breath of a single star. Often it is the record of a system, one star dying, another star disturbing the flow, dust forming, molecules surviving in dense knots, ultraviolet light carving the ejected envelope into glowing structure. This makes planetary nebulae useful laboratories for the late lives of stars like the Sun, but also for dust production and molecule survival in harsh radiation fields. Dense knots inside planetary nebulae can shield molecules from ultraviolet light, allowing molecular hydrogen and other species to persist inside an ionized shell. Even in stellar death, there are pockets of chemical structure. Supernova remnants are the stellar violence equivalent of what planetary nebulae are to gentle stellar death, and they are physically more extreme, energetically more powerful, and scientifically more complex. When a massive star, more than about 8 times the mass of the Sun, exhausts its nuclear fuel and can no longer generate the outward pressure needed to support itself, it collapses catastrophically. The iron core implodes in less than a second, briefly reaching nuclear density and then bouncing, sending a powerful shock wave outward through the overlying stellar layers. The shock wave sweeps through the star in seconds to minutes, deposits an enormous amount of energy in the outer layers, and drives the star's outer material outward at velocities of 10,000 to 30,000 kilometers per second, a significant fraction of the speed of light. The result is a supernova, an explosion briefly outshining the entire host galaxy, and the expanding shell of stellar material driven outward by the explosion is the supernova remnant. Supernova remnants evolve through several distinct phases. Initially, the expansion is free. The ejected material expands into the surrounding interstellar medium essentially without interaction, its velocity determined by the explosion energy and ejected mass. As the expanding shell sweeps up interstellar material, the swept-up mass eventually becomes comparable to the ejected mass, and the expansion begins to be slowed. The interaction of the fast-moving ejected material with the surrounding interstellar gas creates a complex shock structure, a forward shock driven into the interstellar medium, sweeping it up and heating it, and a reverse shock driven back into the supernova ejecta as the inertia of the swept-up material resists the expansion. Both shocks heat the gas to X-ray, emitting temperatures of millions to hundreds of millions of Kelvin. The Crab Nebula, M1, the first object in the Messier catalog, is the remnant of a supernova observed and recorded by Chinese and Arab astronomers in 1054 AD. At its maximum brightness, the supernova was visible in daylight for about 23 days, reaching a magnitude of approximately -6, comparable to a quarter moon. The Crab is now a roughly 3 by 6 light-year elliptical cloud of filaments and diffuse emission approximately 6,500 light-years away, expanding at about 1,500 kilometers per second. Its unusual blue-white glow comes not from thermal emission, but from synchrotron radiation, photons emitted by electrons accelerated to near the speed of light and spiraling around the strong magnetic field lines threading through the nebula. The energy source maintaining this non-thermal emission is the central pulsar, a rapidly rotating neutron star, the collapsed remnant of the massive star that exploded, spinning 33 times per second and radiating enormous rotational energy that accelerates particles throughout the nebula. The Crab pulsar and its surrounding nebula form what is called a pulsar wind nebula, an object category defined by the Crab itself. The Cassiopeia, a supernova remnant, is the most intensely observed young remnant in the galaxy, the remains of a supernova observed on Earth, apparently by the astronomer Royal John Flamsteed in 1680, though the identification of his observation with Cassiopeia A is uncertain, and now appearing as a roughly circular ring of bright X-ray and radio emission about 10 light-years in diameter. Cassiopeia A is remarkable for several reasons. It preserves detailed spectroscopic information about the composition of the explosion products, revealing the chemical yields of the supernova and the nucleosynthetic processes operating in the final stages of the massive star's life. It shows in its morphology the detailed dynamics of the explosion, including asymmetries that preserve information about the three-dimensional structure of the blast wave, and it has been observed repeatedly over decades with X-ray telescopes including Chandra, revealing the detailed structure of the shock systems, and following the evolution of specific features over time. The supernova 1987A remnant in the Large Magellanic Cloud is the closest supernova observed since the invention of the telescope, having been detected on February 23, 1987, and has been studied continuously since. The progenitor star, Sanjalik -69 degrees 202, was a blue supergiant, confirming that massive stars can explode as supernovae in different evolutionary stages than the red supergiants expected by earlier models. The explosion produced the first detected supernova neutrinos. Underground detectors registered a brief burst of neutrinos lasting seconds, arriving before the optical brightening was recognized, confirming the theoretical prediction that the core collapse of a massive star should produce an enormous burst of neutrinos carrying away most of the energy of the explosion. The remnant has since developed into a complex ring system. The optical rings were pre-existing circumstellar structures from the stellar wind of the pre-explosion blue supergiant, and high-resolution Hubble observations since the late 1980s have documented the development of the remnant in real time as the expanding blast wave reaches and illuminates these ring structures. Webb observations in 2023 provided the most detailed view yet of SN 1987A's inner ring and the developing remnant structure, revealing dust formation within the expanding ejecta and the complex interaction of the blast wave with the pre-existing circumstellar material. Supernova remnants play an essential role in enriching and stirring the interstellar medium with heavy elements and dust. Massive stars produce large amounts of oxygen, silicon, sulfur, and other elements before and during their explosions. Iron group elements are made in supernova environments, especially in Type 1a supernovae and in the explosive stages of massive star death. The heaviest are process elements, including much of the gold, platinum, and rare earth elements, are now strongly associated with neutron star mergers, with some contribution from rare explosive environments still studied. The iron in your blood, the iodine in your thyroid, the gold in any ring you may wear, these atoms belong to that wider history of stellar nucleosynthesis, explosive death, and compact object collision. The important point is not that one type of nebula made everything, but that the interstellar medium has been enriched by many channels before the solar system formed. Other supernova remnants show how long stellar death can remain visible. The Veil Nebula, part of the Cygnus Loop, is the remnant of a supernova that exploded roughly 10 to 20,000 years ago. In visible light, it appears as delicate arcs and filaments spread across several degrees of sky, so large that the whole structure is much wider than the full moon. Those filaments are shock fronts seen edge-on, where the expanding blast wave is encountering denser regions of interstellar gas. The shock heats and ionizes the gas, causing it to glow in thin sheets. The apparent delicacy is misleading. The structure is a vast expanding shock wave, still moving through space after thousands of years. The Vela supernova remnant is closer and much larger on the sky, the remains of a massive star that exploded about 11,000 years ago. At its center is the Vela pulsar, a rapidly rotating neutron star. Like the Crab, Vela shows that a supernova remnant is not only ejected gas. It can also contain a compact object, a neutron star or black hole, whose magnetic field and particle wind continue to shape the environment long after the explosion. Supernova remnants are also major accelerators of cosmic rays. The shocks they drive into the interstellar medium can accelerate charged particles to enormous energies through repeated interactions with magnetic turbulence at the shock front. Those cosmic rays then travel through the galaxy, influencing molecular cloud chemistry, ionizing gas in dense regions that ultraviolet light cannot penetrate, and contributing to the energetic particle environment throughout the Milky Way. In this way, The death of a massive star can influence the chemistry inside future star-forming clouds far away and long afterward. They also make dust, destroy dust, and reshape dust. This sounds contradictory, but it is one of the reasons supernova remnants are scientifically complicated. A supernova can condense new dust inside its cooling ejecta. The same remnant shocks can later destroy grains as they collide with hotter gas or sputter under energetic particle bombardment. Webb observations of objects like Cassiopeia A and the Crab Nebula are valuable because they map dust inside remnants directly in infrared light, showing where warm dust lies relative to ejecta, synchrotron emission, and shock gas. Dust is not a decorative detail. It is central to how galaxies cool, form molecules, form planets, and hide or reveal stars. There is a tendency to imagine stellar death as an ending. In physical terms, it is more like redistribution. A star that dies in a supernova sends material outward, drives shocks, accelerates particles, stirs surrounding gas, enriches the medium with new elements, and sometimes triggers collapse elsewhere. The end of one star can help initiate the beginning of another. Protoplanetary nebulae and post-AGB objects occupy a brief transitional phase between the red giant and planetary nebula stages of a dying intermediate mass star, representing the few thousand years during which the stellar wind has just stopped or is stopping. The ejected material is still cool enough to be opaque in the far infrared, and the central star has not yet heated sufficiently to ionize the ejected shell. These transitional objects, also called protoplanetary nebulae, a term unfortunately also used for protoplanetary disks in a completely different context, creating an occasional confusion, are typically highly elongated or bipolar in morphology, suggesting that the asymmetric mass ejection driving the departures from spherical symmetry has already begun. They are bright infrared sources detectable by IRAS, ISO, Spitzer, and Herschel, with the central star still obscured by dust, but the overall structure visible in the near-infrared and optical for the less dusty examples. The Egg Nebula and the Red Rectangle are among the most striking examples, both showing dramatically non-spherical morphologies with jets, arcs, and dust lane structures visible in Hubble images. The Egg Nebula, CRL 2688, is a protoplanetary nebula showing two bright lobes of scattered light separated by a dark, equatorial dust lane and a series of concentric, incomplete arcs embedded in the lobes. The arcs are interpreted as shells ejected at intervals during the thermal pulse episode of the asymptotic giant branch, each pulse driving a brief intensification of the stellar wind that produces an enhanced density shell in the expanding material. The regular spacing of the arcs encodes the timing of thermal pulses roughly once every few thousand years, providing a record of the stellar evolution history in the geometric structure of the ejecta. The overall bipolarity of the Egg Nebula reflects the same binary or magnetic field mechanisms that produce bipolar morphologies in fully developed planetary nebulae. The study of nebulae has been transformed over the past decade by the James Webb Space Telescope, which has revisited essentially every major class of nebular object with unprecedented sensitivity and spatial resolution at infrared wavelengths. Webb's specific capabilities, its large primary mirror, its stable thermal environment at the Earth-Sun L2 point, and its instrument suite covering wavelengths from about 1 to 28 micrometers, make it uniquely suited to study the dusty, dense environments of molecular clouds and the infrared bright features of all nebular types. Webb's images of the Carina Nebula, released in July 2022 as one of the first public science release images, showed a towering cliff of molecular cloud material lit from behind by a brilliant star cluster, with dozens of jets from young stellar objects embedded in the cloud visible as red streaks pointing away from the cloud surface. jets that had been invisible at optical wavelengths because of the intervening dust, but that became spectacularly visible in Webb's infrared cameras. These jets, Herbig Haro objects, named after the two astronomers who first cataloged them, produced when protostellar outflows collide with surrounding molecular material and produce bright emission features at the point of impact, are signposts of active star formation, and their prevalence in the Webb Carina image confirm that this region is actively forming stars at a far greater rate than optical observations alone had revealed. Webb's imaging of the Tarantula Nebula in the Large Magellanic Cloud, the most intensely star-forming region in the local group of galaxies, discussed in the Milky Way episode, showed the region in near-infrared light with a clarity and depth that allowed the identification of hundreds of newly formed stars still partially embedded in their birth clouds, and revealed previously unknown features, including diffuse infrared emission from hot dust heated by radiation from the central star cluster. The comparison between Webb's Tarantula images and earlier Hubble, Chandra, and Spitzer images of the same region demonstrated how much additional information becomes accessible at infrared wavelengths compared to the optical and ultraviolet bands where most previous detailed nebular studies had been conducted. The Webb era has also made nebulae newly useful as bridges between nearby astrophysics and distant galaxies. When Webb studies the Orion bar, the bright interface in the Orion Nebula where ultraviolet radiation from young stars meets dense molecular material, it is studying a photodissociation region in extraordinary local detail. The same kind of interface exists in star-forming galaxies across the universe, but at great distances it is blurred into unresolved emission. Orion is close enough that Webb can resolve the layers: ionized gas, atomic gas, molecular gas, dust grains, aromatic molecules, and embedded small-scale structures. That detailed local physics becomes the key for interpreting the unresolved infrared light of distant galaxies. The Horsehead Nebula plays a similar role. Its edge is a nearly side-on photodissociation front, which makes it one of the cleanest natural laboratories for studying how far ultraviolet radiation erodes molecular gas and changes dust. Webb's 2024 images resolved structure at the illuminated edge with unprecedented sharpness, including filaments and emission from molecular hydrogen and dust. The Horsehead is famous because of its shape, but scientifically it is valuable because of its geometry. Cassiopeia A and the Crab Nebula offer the equivalent laboratories for stellar death. Cassiopeia A is young enough that the ejectas still preserve details of the explosion and the progenitor star structure. Webb has mapped dust, ejecta, and shock material in infrared light, revealing features that are difficult to study in optical images alone. The Crab, powered by its central pulsar, shows how a compact remnant can fill a nebula with synchrotron radiation and shape dust and filaments from inside. Together, these remnants show that a supernova is not a single flash. It is an event whose aftermath can remain physically active for centuries and scientifically useful for much longer. This is why returning to famous nebulae with new telescopes is not repetition. Orion, the Pillars, the Horsehead, the Ring, the Crab, and Cassiopeia A were not solved by being photographed once. Each instrument asks a different question. Hubble revealed optical structure. Spitzer and Herschel traced infrared dust and cold material. Chandra traces X-ray gas and compact object energy. ALMA maps cold molecular gas. Webb connects dust, molecules, embedded stars, and infrared emission at a resolution that fills a previous gap. The same nebula can remain scientifically new for generations. For planetary nebulae, Webb has revealed the fine structure of several well-known objects with new clarity. The Ring Nebula, re-imaged by Webb in mid-infrared and near-infrared in 2023, showed an extraordinary level of detail not seen in previous images. Concentric rings in the outer halo of the nebula, fine radial spokes of emission from knots within the main shell, and the bright inner region showing multiple nested structures invisible in optical images. The near-infrared image additionally showed the central white dwarf clearly and the surrounding environment in detail that allowed the physical structure of the nebula's inner regions to be constrained far better than before. The images were a compelling demonstration of what Webb adds to the study of well-known, previously studied objects, not merely faint sources at high redshift, but nearby, familiar structures that reveal previously hidden layers of complexity under Webb's infrared gaze. There are a few misconceptions about nebulae that are worth clearing away because they change how the images should be imagined. First, nebulae are not dense fogs in the human sense. If you were inside many visible nebulae, you might not see a bright wall of gas around you. The gas is extraordinarily thin. The reason nebulae appear bright from Earth is that we are looking through many light years of material, so the emission accumulates along the line of sight. A cloud can be emptier than any laboratory vacuum and still glow visibly when it extends across enormous distances and is excited by powerful radiation. Second, nebulae do not have sharp solid surfaces. A pillar or cliff is a density and illumination structure, not a wall you could stand beside. The edge appears sharp because the transition from ionized gas to molecular gas happens across a relatively narrow region compared with the scale of the image. In physical terms, it is a boundary layer shaped by radiation, dust, and gas density. Third, the timescales are not human. A jet from a protostar may change visibly over years in high-resolution images, and some supernova remnant knots can be seen moving over decades, but most nebular structures evolve over thousands to millions of years. The apparent stillness of a nebula is not true stillness. It is motion too slow for unaided human patience. Fourth, the scale is almost always larger than the image suggests. A small pillar in a photograph may be light years long. A glowing shell may contain enough mass to form many stars. The apparent softness of a nebula image can make the structure feel delicate, but these are enormous regions. The pillars of creation are not little wisps. The Orion Nebula is a cavity and surface within a much larger molecular cloud. The Tarantula Nebula is hundreds of light years across. Understanding these misconceptions makes the images more, not less, impressive. The truth is stranger than the fantasy. Extremely thin gas, spread across immense volumes, glowing because atoms are being ionized and recombined, because dust is scattering and radiating, because shock waves from stellar death are still moving through space. The strongest way to hold a nebula in the mind is to imagine it at several scales at once. At the largest scale, a nebula is part of the galaxy's gas cycle. It is one feature in a spiral arm, one knot in the Milky Way's larger flow of gas and stars. At the cloud scale, it may be tens or hundreds of light years wide, massive enough to form thousands of stars. At the filament scale, it becomes a network of denser threads, some stable, some collapsing. At the core scale, gravity begins to isolate a future star. At the disk scale, dust and gas begin arranging themselves into the material from which planets may form. At the grain scale, chemistry is happening on icy surfaces. At the atomic scale, electrons are being stripped, captured, and released in photons. The same object can be a cloud, a nursery, a chemical factory, a radiation laboratory, a shock front, and a future planetary system depending on the scale at which it is examined. That is why nebulae work so well for a calm science episode. They are visually gentle but intellectually deep. The subject can be entered through beauty, but it does not end there. The beauty leads to physics. The physics leads to chemistry. The chemistry leads to planets. The planets lead to the conditions for life. The object that first looked like a colored cloud becomes a map of how ordinary matter becomes meaningful structure. A good way to understand nebulae is to stop treating them as separate categories and start treating them as different moments in a flow. Cold molecular clouds are the stored material. Dense cores are the moment gravity begins selecting future stars. Protostellar jets are the first visible signatures of formation. Emission nebulae are what happens when the first massive stars turn on and flood their environment with ultraviolet light. Reflection nebulae show where dust scatters nearby starlight rather than being ionized by it. Dark nebulae show where the material is dense enough to hide what lies behind it. Planetary nebulae show the late return of material from stars like the Sun's supernova remnants, show the violent return from massive stars, and the shock waves that stir the galaxy afterward. None of these states is permanent. A molecular cloud disperses. An emission nebula fades when its massive stars die or when the gas is blown away. A planetary nebula expands and becomes too thin to see. A supernova remnant merges into the interstellar medium. The categories are human labels placed on temporary phases of matter in motion. This makes nebulae unusually honest astronomical objects. A planet can look stable. A star can appear fixed. A nebula makes change visible. It is visibly temporary. It is often being torn apart by the very stars it forms. It is glowing because energy is passing through it. It is dark because dust is gathered there before the next transformation. It is a reminder that the galaxy is not a static arrangement of lights, but a working system. Nebulae are also one of the most direct ways to understand why astronomy is not only about distance. It is about ancestry. The atoms in a living body are not isolated from these clouds. They came through them. The solar system formed from enriched interstellar material. That material had been processed by earlier stars and dispersed by nebulae and remnants. The calcium in bone, the oxygen in water, the carbon in organic molecules, the silicon in rock, the iron in blood, all of it belongs to a galactic history in which gas became stars, stars became enriched gas, and enriched gas became new worlds. The most beautiful thing about a nebula, then, is not only its shape or color. It is the fact that the shape and color are evidence of a process that eventually makes planets possible. A nebula is not separate from us in the way it may first appear. It is distant, yes. It is enormous, yes. It is not alive. It is not aware. But it belongs to the same material story as Earth. When we look at a star-forming nebula, we are looking at matter before it becomes sunlight and planets. When we look at a planetary nebula, we are looking at matter after a star has finished returning part of itself to space. When we look at a supernova remnant, we are looking at the violent distribution of elements without which rocky planets and biological chemistry would not exist. The galaxy does not make life directly. It makes the conditions from which life can eventually arise. Nebulae are among the places where those conditions are assembled, enriched, mixed, scattered, and renewed. There is one more connection worth making explicit. Nebulae are not only about distant stars. They are also about the origin of the solar system. The Sun formed inside a molecular cloud about 4.5 billion years ago. That cloud is gone now. It was dispersed long ago by radiation, winds, and the motions of the stars that formed from it. We cannot point a telescope at the Sun's birth nebula, but meteorites preserve clues about it. The oldest solids in meteorites, called calcium-aluminium-rich inclusions, formed at the very beginning of the solar system's history. Their isotopic compositions show that the newborn solar system inherited material from earlier stellar generations and may have been influenced by nearby massive stars. Some short-lived radioactive isotopes found in early solar system material, especially aluminium-26, tell us that the solar system formed in an environment enriched by recent stellar nucleosynthesis. Aluminium-26 decays quickly on astronomical timescales, with a half-life of less than 1,000,000 years, so its presence in early meteorites means it was added not long before the first solids formed. One possible source is a nearby massive star or supernova in the Sun's birth environment. Another possibility involves winds from massive stars. The exact origin is debated, but the implication is clear. The Sun did not form from untouched primordial material. It formed from gas and dust already shaped by earlier stars. That is what nebulae make visible elsewhere. When we look at Orion, Carina, or the Eagle Nebula, we are seeing environments that may resemble, in broad outline, the kind of clustered star-forming region from which the Sun emerged. Not identical, of course. The Sun's actual birth cloud had its own mass, chemistry, radiation field, and neighborhood. But the basic processes are the same. Molecular gas collapses, stars form in groups, disks appear around young stars, massive neighbors influence the environment, and within some disks, planetesimals begin to assemble. This gives nebulae a personal relevance that is easy to overlook. They are not merely distant clouds where other stars are born. They are examples of the process that produced our own star. The sunlight falling on Earth today began in a star that formed inside a nebula that no longer exists. The planets formed from a disk that condensed out of that same cloud. The atoms in our rocks and oceans had already passed through earlier stellar lives before the solar system began. A nebula, then, is not only a place where stars are born. It is a place where histories like ours become possible. Let's step back before we close and think about what nebulae mean in the broadest sense, their role in the galaxy's history and in the story of everything that has ever lived on Earth. The galaxy is a machine for processing matter. Stars form from the interstellar medium, burn hydrogen into helium, then helium into carbon and oxygen and neon. Then in the most massive stars continue up the periodic table to iron, where nuclear fusion becomes thermodynamically unfavorable and the process ends in a supernova. The supernova returns the processed material to the interstellar medium, enriched in elements heavier than those present before. The next generation of stars forms from this enriched medium, repeating the process with a slightly higher heavy element content. Over 10 billion years of this galactic chemical evolution, 10 billion years of stars forming, burning, and dying. The interstellar medium has been progressively enriched from the almost pure hydrogen and helium of the Big Bang to the element-rich mixture that produced the solar system 4.5 billion years ago, a mixture rich enough in carbon, oxygen, nitrogen, silicon, iron, and dozens of other elements to form rocky planets, organic molecules, and eventually life. Every nebula is a chapter in this story. The dark molecular cloud forming new stars is the beginning of the chapter, the raw material being assembled. The Emission Nebula is the middle of the chapter, the newly formed massive stars illuminating and reshaping the cloud. The Planetary Nebula is the end of one thread, the gentle return of processed material from a dying intermediate mass star. The supernova remnant is the violent end of another thread, the explosive return of the most processed, heaviest elements from the death of a massive star. And scattered through the interstellar medium, mixed and remixed by turbulence and gravity and shock waves. The return material waits for the next cold cloud, the next gene's mass instability, the next protostellar collapse. The atoms in your body have been through this cycle multiple times. Not once, not in a single star, but in a series of stars, each generation inheriting the nuclear products of all the previous ones, each generation adding to the accumulation of heavy elements in the galaxy. The carbon in you was formed in the cores of earlier red giant stars and dispersed in their stellar winds and planetary nebulae. The oxygen was formed in massive stars and dispersed in supernovae. The iron in your blood was formed in the final seconds before a massive star's core collapse, or in the white dwarf detonation of a Type 1a supernova, and scattered across light years. You are, in this literal and physical sense, the cumulative product of multiple stellar generations. The galaxy has been cycling matter through stars for 10 billion years to produce you, to produce the specific mixture of elements and molecules that assembled, on this particular planet, into the chemistry of life. The nebulae are where that process happens, where you can watch it, the nurseries where stars are born, the burial grounds where they return what they've made. It is a cycle that has been running for longer than the Earth has existed, and that will continue for longer than the Sun will last. The Orion Nebula is forming stars right now, tonight, as it has been for the past few million years. The planetary nebula around a dying star is expanding somewhere in the galaxy at this moment. A supernova remnant is cooling and dispersing its enriched material into the next generation's molecular cloud. The galaxy breathes, and the nebulae are where the breathing is visible. That is the strongest way to understand them, not as isolated clouds, not as cosmic scenery, but as the visible circulation of matter through time. A nebula may be quiet in a photograph, but it belongs to a process that never stops: gas cooling, stars forming, radiation carving, dust shielding, shocks expanding, atoms returning, chemistry growing more complex, and new systems beginning from the remains of old ones. Time is the other invisible ingredient. A nebula image often compresses incompatible timescales into one frame. The light may have traveled for thousands of years before reaching us. The stars inside the image may be only a few 100,000 years old. The cloud that formed them may have existed for millions of years before collapse began. The elements in the dust may have been made in stars that died billions of years earlier. A single image, therefore, contains several clocks at once: the clock of light travel, the clock of star formation, the clock of cloud dispersal, and the clock of galactic chemical evolution. This is part of what makes nebulae so calming without making them simple. They show movement at a scale too slow to be anxious. A shock front advances. A pillar erodes. A protostar clears its envelope. A shell expands from a dying star. A supernova remnant cools. Nothing is frozen, but nothing is hurried. Human time is almost too short to notice the motion directly, yet the motion is everywhere. The same is true of the matter itself. A hydrogen atom in a molecular cloud may become part of a star, then part of a stellar wind, then part of another cloud, then part of a planet's atmosphere. A carbon atom may spend time in a red giant, in interstellar dust, in an organic molecule inside a disk, in a comet, in an ocean, and eventually in a living cell. These paths are not planned. They are the consequences of gravity, chemistry, radiation, and time. Nebulae make that circulation visible. They are not still lives. They are slow motion. There is one final reason nebulae remain so powerful for astronomy. They connect what is visible to what is usually hidden. A star by itself shows light. A nebula shows the environment that made the star and the environment the star is changing. It lets astronomers study not just objects, but relationships: star to cloud, radiation to dust, gravity to turbulence, chemistry to temperature, death to future birth. That is why these clouds keep returning in the history of astronomy. New telescopes do not replace the old images, they reopen them. The same region becomes a different object when viewed in another wavelength, with another instrument, at another level of sensitivity. What once looked like a soft glow becomes filaments. What looked like a dark patch becomes a cold, dense core. What looked like a smooth ring becomes thousands of knots and arcs. The universe was not simpler before we looked more carefully. It only appeared that way from a distance. Nebulae reward attention because they become more meaningful the longer they are studied. The first glance gives beauty. The second gives structure. The third begins to reveal the life cycle of matter itself. They are quiet only from far away. Up close, in the language of physics, every nebula is active, cooling, glowing, collapsing, dispersing, shielding, eroding, and carrying matter from one stellar generation into the next. Let that be the last thought before sleep. The galaxy, quiet and enormous, cycling its matter through stars and clouds and nebulae, building slowly toward greater chemical complexity with each generation, working over billions of years and countless stellar births and deaths towards something like the chemistry of a planet, and then the chemistry of a cell, and then something that can look up from that planet and recognize, in the diffuse glow of a distant cloud of gas and dust, the process that made it. Good night.